Hey science nerds, let's talk science, maths, big numbers and little numbers, which is still really exciting. I love scientific notation so much. So, here we have we're treating this with the reverence and respect it deserves, the Hubble Deep Field Image. Now, might be the Ultra Deep Field Image, but I'm pretty sure it's just the Deep Field Image. Every single point of light you see on there is a galaxy. And there's about 10,000 of them. And the way it is they had the Hubble telescope up there, and they just opened the camera lens, and they opened it for ages, so that lots and lots of light was able to get in. Boom, away we go. Now, as I say, sorry, it's really cool. So, here we have the Hubble Deep Field Image. There are about 10,000 points of light. And each point of light here is a galaxy. And those galaxies are home to hundreds of thousands, or hundreds of millions, of stars. So based on this, we can look at how many stars are here. And the amount of stars in this section of the image, which is most of it, a little bit cropped out for the shape, whatever, doesn't matter. This section of the image has 10 quadrillion stars, or 10 billion stars. So that means they counted all the stars. Well, they can count it, whatever, but you get all the stars of 1, 2, 3, 4, 5, all the way along to 1 billion. And then at that billion, you do that, so you recount that another 10 billion times. So there are 10 billion stars, or 10 quadrillion stars. Now, that's this number here. There's 10 with 15 zeros after it. So 10 with 15 zeros. That's a big number. Now, what this means is, that's an awkward number to write down. It's an awkward number to do maths. So, we can write it in scientific notation as 1 times 10 to the 16th. And all of a sudden, this number is much less intimidating. Still impossible to visualize, but actually able to do maths with, sort of in our heads and in a more simple way. And that's why we use scientific notation. Because sometimes numbers are redonkulous, whether they are redonkulously little or big. And that makes them exciting. So here's your vocabulary for the lesson. If I can get you to pause the video, write this down, refer back to it as we're moving along, and so forth. You'll have this to come back to, and we won't need to keep going, what does this mean, Mr. Whiting? And I'll tell you, but it's a video. I can't hear you. So, scientific notation. We use it with large ungainly figures, either really many digits, small or so in the negatives or in the decimal places, or in the really large numbers, or just as importantly, to show significance and precision, how accurately we've measured something. So if we've measured something to be 20,000 kilograms, but we only measured it to the nearest ton, so that means we've got to 220, those numbers afterwards, they're not, so 20, and those 3 zeros after that are not significant. So if we were to use scientific notation, we can show 2.0 times 10 to the power of 4. We can show how accurate our measurements is. And what that means is that, yes, we've got it down as 20 tons, but it's somewhere between 20.499 or 20.5 tons and 19.5 tons. So somewhere in that range. So let's look at an example. We've got 7.2 megaliters. And this needs to be converted to liters for a calculation. Makes sense? So that becomes 7,200,000 liters. Cool, but this is an awkward number and gives a false impression of accuracy. For example, we know that this is accurate to the nearest 100,000 because that's what it was there. Okay, so we want to convert this to scientific notation. Now, write only the significant figures. This is a step-by-step thing. Write only the significant figures. And you only want one figure to the left-hand side of that decimal place. Okay? And that'll look like this. 7.2. Just like it started, nice and simple. Then, we want to work out the factor. So this is 10 times, so we've got 7.2 times 10 to the power of n, where n equals the number of places the decimal place had to move. It's positive if it moves to the left. It's a negative number if it moves to the right. Okay, so this becomes 7.2 times 10 to the power of 6. And that's because decimal places here, it goes 1, 2, 3, 4, 5, 6. 7.2 times 10 to the power of 6. Now, with the positive one. So let's check our understanding here. First off, we want to convert 32 kilograms to grams. Okay. First thing we do is write down the whole number in grams. It's a big number. Then we want to write down just our significant figures, which would be 3.2, and then it's times 10 to the 4, because 1, 2, 3, 4. Now this is a bit trickier than the last one because we've gone from 32 to 3.2. Often when people say kilogram, they go, oh, cool, that means 10 to the power 3, because it would be, if it was in kilograms, it would be 1, 2, 3, so 32 kilograms. But remember, we're going grams, so 3.2 grams times 10 to the power 4. Now, we want to go from 62.9 micrograms. This is going to be a bit awkward, and we'll see why. To grams. So the very first thing we do is we write down what this whole number is going to be. Grams, okay, 0.0000629 grams. Then we write down the first significant numbers, which are 6.29, and we have one number to the left of the decimal place, and then we multiply it by how many places we have to move the decimal place. And here the decimal place actually goes 1, 2, 3, 4, 5, but it moves to the right, and that puts a little negative power up there as well. All right, I hope that made sense. If you have any questions, put them in the comments below, and we'll get back to you as quick as we can. Thanks for watching, and we'll see you next time. Bye now.